Hi everybody, Ken the Metal Professor here with a new entry in the sequence of videos that used to be today on Math Reddit, but normally what I was calling today was actually picking posts from a day or a couple of days ago. So this has been recently renamed Recently on Math Reddit so that I can spend a few days finding things that are interesting to talk about based on posts on the Ask Math and Learn Math subreddits. I like to pick problems that are relatively quick to answer, but also open up the chance to talk a little more generally about something that's interesting. So over the last few days, I came across a couple of examples like this. I actually came across a lot, but these are the two that I've picked. A user, Representative Ask230, asked about a problem related to something called Gaussian Elimination, and that Void Boy on the same subreddit asked a question which turns out to be equivalent to doing an epsilon-delta proof of a limit. So let's take a look at these. The first one was posed as we want to solve this system of 3 equations and 3 unknowns. How do we go about Gaussian elimination? What's the overall strategy? How do you keep it straight from problem to problem? So I'm going to assume that if you're watching this, that I can breeze past a couple of the very introductory comments about Gaussian elimination. I'm going to take the 3 equations and explicitly put in terms that have coefficients of 0 so that we can see the structure. And then I'm going to rip those constants out from both sides of the equal sign and place them into the augmented coefficient matrix here. The idea of Gaussian elimination is that, back in Algebra 2 or something, everybody learned how to solve 2 equations and 2 unknowns and 3 equations and 3 unknowns by substitution or by elimination. And it turns out that the important information in this system is the coefficients, right? The variables, it doesn't matter what they are. So we don't really need to see them. We just have to agree in the ordering that they've been placed in the equations. And so this augmented coefficient matrix is just the table of numbers that represents the coefficients. And every row in this augmented coefficient matrix is an equation in disguise. You just have to remember what the variables were and where the equal sign went. And that would be between this 3rd and 4th column. Now, the idea of elimination is to play a game with the numbers in this matrix to reduce it to basically the identity matrix. In other words, having 1s down this left diagonal and 0s everywhere else. And then the numbers that survive in the right-hand column are an indication of the solution to the system. There's a lot of details there that we're not going to get into. We're just going to practice the overall strategy here. There are 3 rules. You're allowed to multiply any row by a constant, because if we go up and pick out one of these equations and we multiply the equation on both sides by any constant, the equality holds up, right? We are allowed to add 2 rows together and replace either one of the rows with that result. And we are allowed to interchange the position of rows, because up here, the solution to this system is the same solution regardless of what ordering the equations have, right? So with those 3 rules, the strategy is to try to make constants turn into zeros. And so the first one we'll try is indicated here. This number 1 at the top is an arrow, and we're going to try to shoot out the 2, which is its target. Remember that we're allowed to multiply rows by constants and then add 2 rows together and replace one with the results. So we would say, boy, it would be cool if this blue number 1 turned into a -2, because then when we added these rows together, 1 and 3, the new row that we create would have a 0 in that spot. And so when we place that into row 3, this 2 has turned into a 0. So in other words, we're going to do -2 times row 1 plus row 3, and then put that result into row 3. in accordance with the rules of this process, that is actually a sequence of 3 moves. Multiplication of row 1 by -2. That's legit. Take that new row and add it to row 3. But we don't want to replace row 2 permanently with row 1 times -2. So having done those first 2 subtle steps, we can just go back to row 1 and multiply it again by -1/2, and that resets it to what it was to begin with. So when we say -2 row 1 plus row 3, and that goes into row 3, that's actually a little cluster of mini operations, but they're all legal, and that's the point. So when we do that, here's the new result, the second matrix here. So -2 times the first row plus the third row. So -2 of these plus this red 2, that's your 0 down here. -2 times this entry of -2 gives us a 4 plus 0. There's our 4. -2 times 0 plus -1, still -1. -2 times this entry becomes +2 plus -8. There's your -6. Now we proceed. Again, we want numbers on the diagonal to survive, but we would like numbers off the diagonal of this left square part of the matrix. Those want to be turned into 0. So again, we have an arrow and a target. The blue 2 is the arrow, the 4 is the target. So we could say, wow, wouldn't it be great if this blue 2 suddenly became -4 so that we can add these 2 rows together and produce a 0 in the spot held by the 4. And so -2 row 2 plus row 3 into row 3. How about that for a move? Now we have to be careful because we could also say, well, ooh, here's already a -2. What if we multiplied row 1 by +2? That would turn this into a -4 and add that to the red 4. To make a 0. Why not do that? Well, that would spoil this 0 that we already worked so hard to put in place. So we do not want to involve row 1 in this new operation. So again, here was the previous result. Apply that row operation of -2 row 2 plus row 3 into row 3, and here's the result. And now we can just do a little housekeeping if we would like. Remember, we can multiply a row by any constant we want. Now, multiplying by 0 would always be useless. But if we took row 2 and multiplied across by 1/2, took row 3 and multiplied by -1/5, that's going to tidy this matrix up a bit into this form that's now at the bottom of the screen. Okay, so we can pause here and say, well, what was the question? If the question was just, what's the solution to this system? This might be a good time to jettison from the Gaussian elimination process and just develop the equation's solution. Because this bottom row, and remember, every row is just an equation in disguise, this bottom row currently says 0x plus 0y plus 1z equals 2. Well, that's just z equals 2. The second equation is y plus z equals 1. And now if we know that z is 2, now we can do a real quick calculation to figure out y. And then this top equation, if we know the value of y, we can quickly gather the value of x. And so the bottom row tells us z equals 2 explicitly. Climb up to the second row, we can dig out y as -1. Climb up to the top row, then we can dig out x as -3. So now we know the solution to this system is -3, -1, and 2 for x, y, and z. If the question was just get the solution, there we go, we're done. If the question was put this matrix in reduced row echelon form so that we can see the solution explicitly in the coefficient matrix, then we have more work to do. So let's keep going. And I don't know what the original phrasing of the question was, but let's just say it was get reduced row echelon form. That's the one where we have 1s down this main left-hand diagonal and 0s everywhere else. And then whatever's in the right-hand column is whatever it is, and that helps us learn the solutions. So let's keep going with the elimination. Having produced this lower corner of 0s, now let's move above the diagonal and get rid of this -2 that's in red. We're going to use the blue 1 as the arrow. So how about 2 row 2 plus row 1 going into row 1? There's the result. And now we have this 1 in the lower corner of the diagonal on the left. We're going to use that to take out both of the red digits above it. So 2 operations, row 2 plus negative row 3 into row 2, and row 1 plus negative 2 row 3 back into row 1. If you want to work this out for yourself, obviously you just hit pause and do it. But here is the result. And now again, remembering that every row is an equation in disguise, row 1 says 1x plus 0y plus 0z is negative 3. That's x equals negative 3. Similarly, y is negative 1, z is 2. And ta-da, there's our solution one more time. Okay, now overall, here is the strategy for Gaussian elimination in the 3x3 case. The diagonal on the left-hand square should eventually develop, hopefully, into 1, 1, 1. Okay, but more importantly than that, we want to introduce zeros into these spots that are counted off with red digits, and we want to eliminate them in the order that they're shown here, unless there's a clever reason to do otherwise. But if you're just trying to, just not overcomplicate things and just do the same thing every time, we would eliminate this spot first, eliminate spot number 2 next, eliminate spot 3, and by eliminate, we mean turn into 0 using those legal row operations, then do spot 4, then spot 5, then spot 6. And then when you're done, you have zeros off the diagonal and non-zero numbers, or maybe some zeros, on the diagonal, and those can be scaled down to ones very quickly. And that's one of the things that I saw tripping people up the most, is that people get hung up on making sure these diagonal entries become ones, and sometimes people force that way too soon, which then introduces yucky fractions and makes things gross. Okay, so in general, don't worry about putting ones on the diagonal until the bitter end. So for example, if this new matrix that's here was a work in progress, somebody who's focused on the diagonal might want to multiply row 1 by 1/3 and multiply row 3 by 1/4. That does put ones on the diagonal, but imagine the fractions that are now in place in the other locations. And now you're going to have to carry that baggage around as you proceed with your elimination. Okay, so don't do that. Keep things as integers as long as you possibly can. And then at the very end, if you have like a 3, 0, 0, 13, now you can divide row 1 by 3, or properly said, multiply it by 1/3. To get a 1 in this place. But make that the last thing that you worry about. Now, in the problem we just did, let me find it here. Where did it go? Nope, I lost it already. Wait, it was way back here, wasn't it? Okay, here I did a little bit of scaling prematurely, but it was clean, right? Row 2 was 0, 2, 2, 2, and here I said, okay, if I multiply this row by 1/2, I've still got integers, and in row 3, I can clean it up and leave behind integers. So I did do those at the proper time, but if I was going to generate fractions over here in this quadrant of the matrix, I don't think I would have done that. But that's the overall strategy of Gaussian elimination. All right, problem number 2. Obviously, this is going to be a long video, but that's why I picked these problems, because they open up the door for a little bit more discussion and explanation than just here's how it's done kinds of things. This question turned out to be what I'm assuming was a problem of doing an epsilon-delta proof for a limit of a sequence. But the problem as stated was just prove that there is some natural number n so that this inequality holds whenever the value of little n is bigger than this chosen value. Now that's, if you haven't seen this stuff before, this is going to be a headache, and I don't know if you want to watch it. But if you have seen this before, or even if you're just curious, what we're doing here is we're proving that in a sequence of numbers built as 2n over n plus 5 for integers n starting at 1 or 0, As n goes to infinity, the limit of the values in this sequence is 2, meaning as n gets bigger and bigger and bigger, the values coming back from 2n over n plus 5 are getting closer and closer to 2. That's what a limit is. If we swapped n for just like the regular variable x, this is equivalent to showing that the limit of the function 2x over x plus 5 as x goes to infinity is 2. Okay? Here's a picture and then a table of this idea. Maybe I'll show the table first. What I've done here is I've just listed out some values of n, and I've calculated 2n over n plus 5. So when n is 1, 2n over n plus 5 is 1/3. When n is 2, 2n over n plus 5 is 0.57, etc. So n gets bigger and bigger and bigger, and then in column D, you can see the cascading results. And those results sure look like, as n gets bigger and bigger, they're getting closer, the results are getting closer and closer to 2. Right? Here is a picture of that. It's not a good picture, but it's a picture. This curve is either the function 2x over x plus 5, or if you follow the dots, those are supposed to be representations of the value of 2n over n plus 5 when n is 1, then 2, then 3, then 4, and so on. Okay, so this sequence or this function, as the input gets bigger and bigger, so as we choose values farther and farther out the horizontal axis, the value of the result, 2n over n plus 5, is creeping up on 2. And what the question as posed is looking for is basically a threshold here, where we can say that suppose we've specified the size of a little bitty window just below 2. I can then find a location on the horizontal axis which will ensure that as long as I'm picking my n's or my x's from beyond that threshold, then every result that I get for the values of this sequence or this function are going to be, quote unquote, that close by epsilon to 2. Oh, sounds like the dogs are about to get a walk and they're excited about it. So if you hear barking in the background, that's what's going on. Okay, so it's almost like a call and response or a challenge. Epsilon is something that is handed to us. Somebody says, I don't believe that the limit of this sequence, 2n over n plus 5, I don't believe that this is getting closer and closer to 2 as n gets bigger and bigger. And we would say, well, yes, it is, because the results do get closer and closer to 2. In math, we have to be very particular about how we say things. So how do we measure close? Right? And here's how the skeptic could do that. The skeptic could say, okay, fine. I want you to get me within 0.1 of 2 for every single result beyond a certain place. And we would be able to say, you know, calculate, okay, as long as we start picking values bigger than 5,000, we're always going to be within that range of 2. And the skeptic could say, well, that wasn't very impressive. I want you to get me within 0.0001 of 2. And we would be able to say, calculate, okay, as long as we go out to values of the input bigger than 67,594, the result of this 2n over n plus 5 is going to be within 0.0000 whatever of 2. In other words, whatever epsilon we are given, we have to be able to decide what threshold for the input value we need to set so that once we're beyond that input value out here, we are landing within epsilon of 2. Okay? And this is all about knowing how to measure that. I'm going to pause for a sec because the dogs are getting really obnoxious. Okay, now they're outside. So their barking should be dwindling off. So the statement we're trying to demonstrate is that given some value of epsilon, it needs to be positive because it's measuring closeness to 2, we want to make sure that the distance between the result, 2n over n plus 5 and 2, is less than that epsilon. That distance is what this measures, right? This measures how close are we to 2? Whether we're below it, whether we're above it, the absolute values take care of that. So given we're handed this epsilon, 0.1, 0.01, whatever it is, the challenge value. We want to go locate some threshold for our input value so that whenever our input is bigger than that threshold, we are now guaranteed that we are within epsilon of our target limit value of 2. Okay. Now, the thing about these statements is they almost solve themselves if you shake them out a little bit. We want to come up with a relationship between this threshold value and the epsilon that we're handed. So if we're handed epsilon as 0.01, we go boop, boop, boop. Okay, here's our threshold value. If we're handed epsilon as 0.0000498, boop, 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 here's our threshold value. We want a little recipe for our threshold value based on epsilon. Okay, so let's just let this statement evolve. Given an epsilon, we want the distance between our recipe and 2 to be less than epsilon whenever we're choosing values farther out than some threshold. Okay, now in this absolute value term, there's 2 terms that might be combined. So let's take that second term and prepare it for combination, and then do that combination, right? We're not really worried about what's happening. We're just evolving this expression. And look, there's some cancellation in that numerator, and there's an absolute value, so we can let it do its thing. Whoops. Yeah, in Adobe, that little bottom bar pops up whenever the mouse creeps too low on the screen. So we're going to let the absolute value do its thing, right? So going from that bottom phrase, the 2 n's are canceled out. Now we have an absolute value of -10 in the numerator, but the absolute value of -10 is just 10. Okay, so here's the evolution of this challenge. We haven't really calculated anything. We've just tinkered with the expression itself. Given this challenge value epsilon, we want to be able to find out a threshold value for our input that ensures this evolved version of the challenge, that 10 over n plus 5 is less than epsilon. Now, how can we get a relationship between n and epsilon? Maybe we can solve for n, right? So let's evolve this a little bit more just by multiplying this expression by n plus 5 on both sides and dividing both sides by epsilon. Okay, and maybe subtract that 5 over. And again, all we're doing is evolving the expression. So given this challenge value epsilon, we're now up to saying we want to have 10 over epsilon minus 5 being less than n whenever n is bigger than some value. Now, if 10 over epsilon minus 5 is less than n, doesn't that mean that n is bigger than 10 over epsilon minus 5? So here's our new statement. Given this challenge value epsilon, we want n to be bigger than 10 over epsilon minus 5 whenever little n is bigger than some mystery value. If only we could say that n is bigger than some mystery threshold value whenever n is bigger than, specifically, 10 over epsilon minus 5. And you see what's happened. We've evolved the challenge statement just by tinkering with the measurement of distance to get a relationship between n and epsilon. So if we're handed an epsilon value, we just calculate 10 over epsilon minus 5. And that's the threshold value that guarantees that 2n over n plus 5 minus 2, that distance will be less than epsilon whenever the input value little n is bigger than this threshold value big N. Okay, we could even make this a little more efficient. In other words, if the skeptic has handed us an epsilon value, we go boop, 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 and we calculate 10 over epsilon minus 5, and we say, well, as long as we're picking input values bigger than 10 over epsilon minus 5, then we're guaranteed that we're within epsilon of 2. And if we're picking values bigger than 10 over epsilon minus 5, then certainly we can pick values bigger than just 10 over epsilon. It's just a little bit farther out. So we can actually clean up our calculation threshold value a little bit. Okay, but that's the payoff. Given a challenge value of epsilon, which is a very, very tiny number, so the skeptic is saying, okay, fine, get me this close to 2. Get me within epsilon of 2. We say, we're just going to go out on the x-axis, the horizontal axis, to 10 over epsilon. And if epsilon is very tiny, 10 over epsilon is going to be very big. As long as we're farther than that, for our input values, the resulting value of 2n over n plus 5 is going to be within epsilon of that limit value of 2. And that's how you prove a limit. You quantify closeness and say, no matter how close to our intended limit we want to be, we can guarantee that we can get that close by going far enough out for our input values. And that establishes the limit. Okay? So all of that gobbledygook, that's what it all means. What I've done here is I've created a little spreadsheet check just to try this out. So column A shows some values of epsilon. The skeptic says, I'll start off easy on you. Show me that you can get within 0.1 of 2 out of this 2n over n plus 5 thing by going far enough out. Well, column B calculates 10 over epsilon. That's what we decided we could do. So when epsilon is 0.1, 10 over epsilon is 100. Now what this value is, that actually makes us our distance to 2 equal to epsilon. We want it to be less than epsilon. So let's go out one more term, to term 101 in the values, the possible input values for little n. We're going to calculate 2n over n plus 5. We're going to measure the distance of that value from 2, and then we're going to go back here and check whether or not that's really less than epsilon. And in this case, it is. There's just a inequality set here that comes back as true if this value is less than epsilon. That is true. Okay, so the skeptic says, well, 0.1, that wasn't so hard. Let's make it worse. I want you to get within 0.01 of 2. Surely you can't do that. And so we say, fine. 10 over epsilon is 1,000. Just going to nudge a little bit past that to make sure that we've inched far enough out there. We're going to go out to input value 1001 and beyond. At the input value of 1001, 2n over n plus 5 is 1.99006. How close is that to 2? Well, it's 0.00994, etc. away, and that's less than epsilon. And if we go farther out than term 1001, these values are going to be even closer to 2. And so the skeptic has given us this challenge threshold, closeness to 2, and we've said, fine, we just have to go out to 1001 or farther, and every result we get is going to be that close to 2. And the skeptic says, you're good at this. Let's get within 0.001 of 2. Well, here's 10 over that value, inch a little bit farther. Here's 2n over n plus 5 for that value. Here's its distance from 2, and is it less than epsilon? That sudden interruption that just happened was because, for whatever reason, my recording bar in Camtasia just vanished. It stopped recording. I went to the directory where it stores the raw recording files, and there was no new file. And I was like, oh my gosh, did I just lose almost half an hour of recording? That's going to be really bad. But when I restarted Camtasia, it told me, hey, there's an unsaved recording from your previous session. Do you want to recover it? I was like, oh, please work, please work, please work. And it worked. Whew. So I got it back, but it does cause this interruption, and it's not worth trying to edit it smoothly. So that's what happened. But anyway, here was the story that was being told, right? We were doing that epsilon-delta proof of a limit of a sequence, and we are successfully able to say that given a challenge value of epsilon, we can ensure that the values of 2n over n plus 5 are landing within that distance of 2, as long as we're picking values for little n bigger than some threshold value. And we learned how to calculate that threshold value given the challenge value of epsilon. And so the end of the video, as I just click back to this slide, right? Given epsilon, we choose n to be 10 over epsilon, and then this right here, which is, see, now let me go back a little bit more. Sorry. There we go. 2n over n plus 5 minus 2, the absolute value of that, that's the distance between the function or the sequence recipe 2n over n plus 5 and 2. That will be less than the challenge value of epsilon whenever we're picking input values for our variable n beyond this calculated threshold value of 10 over epsilon. And the way we did that was just by setting up the challenge to begin with and tinkering with this expression to try to draw out a recipe for n that is based on epsilon. And we got to this one out of the raw data, and we said, well, if we're picking n bigger than 10 over epsilon minus 5, we might as well just pick n bigger than 10 over epsilon and don't worry about that minus 5. And so that's how we got to this. So there's your quick recap after my almost disaster. I would have been really sad if I lost that half an hour of recording, because I was looking forward to doing this today after yesterday when I got COVID vaccine in this arm, flu vaccine in this arm, blood work drawn from this elbow, all within like an hour of each other, and then a couple hours later went to the dentist. So yesterday was pretty gruesome. So talking a little bit of math today is helping me recenter myself. So I hope this was useful to you. If the original posters found it useful, that would be super duper as well.